And if we now start getting a little bit into the specifics, right? We spoke initially about training and what role machine learning has played there. But tell me two things, right? Like one, give us a little bit of a sense of how robots are trained in general and how these approaches have evolved over time, right? Because I remember when I was in college, you used to have stuff like people used to be wearing, some patches of sensors on their arm, and they would move it around, and then you would have a robotic manipulator arm that was sort of mimicking that motion and learning, right? Is my earliest experience with seeing how robots are actually being trained. But give us a general view of how robots are trained, and how these approaches have evolved over time. And if you could also double click a little bit into what is it that's happened of late that's sort of allowing this kind of like unprecedented breakthrough, right? You mentioned that, look, applying the same techniques that we've applied to LLMs to robots is what is really allowing this sort of inflection. But what does that mean, to be specific, right? So how are robots trained in general? How have we evolved? And right now, what's changed about the ability to sort of train robots?
Yeah, so I think if to answer the first part of your question, how has robot learning evolved over time? I think initially the very first approaches at at making robots were using some hard-coded rules, right? So again, if you are making a manipulator arm, for example, it could be that if I detect this object, do this. If I feel this force, if you detect this force that you've hit something, do this, and making a set of rules like that. But you can imagine that this works only in very simple scenarios, very controlled situations. Like how what set of rules can you even describe for a self-driving car, right? Like that, there are infinite situations. And in fact, this is not just that nobody has tried. Like I remember when I took my driver's license test in the US, I was reading through the driving manual, and it literally, like, the official driving manual said something like, it's even though this manual is like a collection of rules and regulations, it is impossible to describe or to make rules for every conceivable traffic scenario, something like that. So right, so people have thought about this for a long time, like outside of robotics, and it's just not something that can be done. So that's one thing. So that those approaches worked, but they were very, very limited. Then the second, I think after that, people started working on like um, uh, kind of these uh, applying machine learning in each of these tasks, each of these areas that I mentioned, like sensing, perception, planning, control. People started applying machine learning individually, right? So they said that, okay, let's make a an object detector to figure out what are the objects around me. Then let's make another model it will take all these object detections, and it will decide, okay, what do I do? Like, do I accelerate? Do I decelerate? Do I turn my steering wheel? Stuff like that. And then finally make another model which will actually convert your commands to like actual torques and stuff like that that go into your motors and things like that. Then this is again like very analogous, right, to computer vision, NLP, where people had different machine learning. Initially, it was all hard coded, then individual machine learning models. Then people were like, okay, why are we doing, like, we are seeing that each of these models are improving with data. So why not just have one giant model that we throw in a lot of data? And that's where we are now, which is that we have, like, a lot of people are betting on like foundational models, like this people if you say that ChatGPT is a foundational model for natural language, or a foundational model for multimodal understanding would be something that you can upload images to and it understands images. So now we're trying to get to um, a foundational model for robotics, which is in many ways a superset of LLMs and vision language models, because it not only needs to understand language instructions and vision, but it also needs to have understanding of actions. So in this, if I see this image, like if I want to pick up a glass in this image, how do I move my hand? How much
Right.
force do I apply? Stuff like that. So it's a strictly harder problem. And yeah, so to answer your question, the second part of your question, I think right now where we are with autonomous robotics, a lot of these a lot of work has gone into having one model do all of the individual pieces that I described. And this isn't specific just to humanoid or these new wave of robotics companies. I think a lot of um, earlier companies, specifically self-driving companies, have already discovered this, that having one model that does the whole thing end to end is better. I think like Tesla gave a talk at a scientific conference where they described that they were doing one full one model for end-to-end driving. I I can't remember if Waymo does that or not, but yeah, there's another company in the UK called Wave. They also do this. So yeah, there's a lot of evidence that this is working well in robotics.
Understood.
Yeah, and so the way I mean, yeah, I can talk a bit more, but yeah, if you about like individual concrete techniques, but yeah, if you have another question, we can put that on hold for a second.
Yep. I think one of the things that I also remember, even when I was in college, that techniques that people were applying to robots in particular was the concept of reinforcement learning, right? And you also see a lot of discussion and commentary around that in the context of LLMs as well. Could you take a couple of minutes, talk to us a little bit about what reinforcement learning is? And what role does it play in robotics? Is it seen as a promising approach? Has it been an integral part of achieving some of these closed loop control systems that you mentioned? Would be helpful to understand.
Yeah, I think so reinforcement learning is basically a particular type of machine learning where and again, like machine learning is just like techniques that how do you learn something useful from data, right? Very broadly speaking. And reinforcement learning is a particular subfield of machine learning, which is like you have some data and you are able to um, assign scores to that data. So
Okay.
you have some autonomous agent, right, interacting with some environment, and you have someone or some entity. It could be a human, it could be another algorithm, which looks at how the agent is behaving and gives it some scores that okay, this was good, this was not so good, this was bad, this was very bad, stuff like that, and the agent uses that feedback to get better. And yeah, reinforcement learning has absolutely been very helpful in robotics. The It's been helpful. So I think the main challenge with reinforcement learning is like by definition, it only works when you have a meaningful reward to give your autonomous agent. So in situations where it is easy to define a reward,
Mm-mm.
reinforcement learning has worked very well. So again, like taking an example from LLMs, if you want your model to solve to play chess, for example, yeah, sorry, not LLMs, but like taking a step back, like before when all these what was uh the I forget, DeepMind had this
Yeah, I think it was
demo driven.
AlphaGo. AlphaGo is the one that you're maybe talking
Correct.
about.
AlphaGo was for Go, yeah.
Yes.
So they used reinforcement learning, and games were a very natural way for reinforcement learning to start because you have a very concrete notion of
Reward
reward.
mechanism. Yes,
Yeah.
yes,
So that's the first kind of stepping stone that people immediately jumped to with reinforcement learning. I think most of research after that has been how do we define rewards for more complicated tasks that we care about.
I see.
Like in driving, for example, it's been somewhat useful because sure, you can assign negative reward when you have an accident, but positive reward for other cases, but it's like how much positive reward do you define? Like
Hmm.
do how do you define good driving? Like what if someone accelerates very quickly, brakes very quickly? You want to not reward that, but sometimes you do want to do that. So it's just like
I understand.
making the reward itself is just so complicated. So I think what I've seen in robotics right now is um, the place where reinforcement learning has worked really, really well is control. So what I mean by control is the part that the last part of the stack that I was talking about, which is that if you know what you want to do, how do you actually do it, right? So for a self-driving car, control is actually not very hard because if you know that, hey, I want to go to this speed and I want to turn at this angle, you just turn your steering wheel to that angle, you hit your accelerator for some amount of time. But for some other complicated, different form factors have much harder control, right? So if you have a robotic arm, for example, control is slightly more complicated because it's like if it has like if you just look at your hand, right? If you want to pick something up, I actually don't have control on the tip of my fingers. What I do have control of is each individual joint. But the human brain is really good at knowing how do I move each individual joint to move my fingers to where I want to go. And that's something that we have solved also. It's like pretty standard techniques. But what's more complicated now is, let's say you have a humanoid robot, right? And you want it to, let's say you want it to climb stairs.
Right.
Now, while climbing stairs, there will be periods when both of its legs are on the ground. There'll be periods when its right leg is on the ground. There'll be periods when its left leg is on the ground. How do you figure out how to um, rebalance weight across both feet? And then when you step up, the weight should be distributed like not just like very gradually across like individual parts of the feet of the foot.
Mhm, mhm.
How do you move the rest of your body? Like you'll have to move your hips if you are
Right, right,
moved. So it's very, very complicated. But that is something where reinforcement learning has really worked is and there's like a lot of academic research on this, but designing very good, robust controllers is something reinforcement learning has worked in because it's like it's relatively easy to define a reward there, right? Your reward is basically, hey, I want the robot to achieve this position of like, let's say, being a ballerina, like, standing up on its toes and raising its hands.
uh-huh,
I
uh-huh.
want the robot to achieve that. So I my reward is how close is the robot to that. And we have simulators which can actually simulate the effect of gravity and friction and stuff like that.
Right.
So you have the robot achieve this position in the simulator, and if it falls, you give it a negative reward. If it stays stable while achieving that position, you give it a positive reward. If it stays upright but it doesn't fully achieve the position, you give it like a medium reward, stuff like that. So that's something that has worked really well because we know how to define rewards in that. We've come up with good techniques and good
Right.
simulation. That's also one thing that some people miss is that simulators have come a long way. Um, Simulators have gotten much better, much cheaper, and also it's again one of these virtuous cycles that like other advances in AI have also made simulation better because with all this GPU computing and stuff like that, a lot of simulations actually used to be very slow, but people have now implemented. simulation algorithms that run really, really efficiently on GPUs. So stuff that would take like minutes to simulate before is now like you can run it in a few seconds on GPUs. So now you
Got
can
it.
do like real-time simulation and things like
Hmm.
that.
Hmm.
So yeah, I think short answer is reinforcement learning has worked very well there, but I think there's still some work to be done to make reinforcement learning work for to solve the other parts of the stack that I was talking about, which is like perception or planning, because it's like if you want your if you want your robot to pick up an object on the table, it's like there are so many things it can do
Right.
in that, and then how do you even decide, like how do you even give it a reward? How do you even detect that it has picked up the object, and then when do you give it a reward? What if it picks it up in an unstable way? What if it picks up while yeah, it's again, it's like self-driving, where defining a reward is very difficult. So that's, I think, something that work needs to be done.
That's actually super interesting. I'd honestly never thought of it from that perspective, right? I think what had always been sort of more on my mind was the whole mechanism through which it understands, and then it changes and tries in a different way depending on what the reward mechanism is. But I never gave much thought to how difficult it is to even design the reward mechanisms, right? That there's a lot of modeling work that's
Exactly.
going on apart from the problem solving itself, which is happening. Was like a really, really interesting take to have. Along the lines of what you were just
Oh,
mentioning. Yeah,
sorry to interrupt. Actually, when you mentioned, I forgot to mention one important point also is
please go ahead.
when apart from the reward is one of the most important things, and then the other thing is also the ability to interact with the environment, because you can only grade something, you can only grade performance when you actually see the agent do something, right?
Right, and measure it,
So
right, in some
yeah, exactly.
way.
So now that acting can either happen in the real world, but that's obviously dangerous. Like if you have a self-driving car that you're trying out in the real world, like it could do unsafe things. So you don't want to
Right,
test it in the real world. So then you are like, okay, let me test it in simulation. But then obviously your simulator is not perfect. There's like a simulation to real gap. Um, then it's also, you also want an algorithm that learns with that doesn't take too long to learn, so it doesn't require too much data.
right.
Otherwise you'll just be interacting with the world and the model will just keep improving very slowly. So those are yeah, answer is like interaction with the world is again something that is a bottleneck, and that's again
Right.
something that either simulation can solve, or if not simulation, you have to do it in the real world, but then you have to do it efficiently, because you can't you might have heard these figures that some people say that, oh, we trained our algorithm for like a million years or something worth of data in simulation. Like,
Right.
sure, if that works for you, that's great. But if you don't have an accurate enough simulator, then like you can play chess in a simulator, but you can't really drive a car in
Sure,
simulation
sure, sure,
accurately.
sure.
So if you apply the same techniques, you'll just never be able to learn. So yeah. Anyway, that's yeah.
I think that makes a lot of sense, right? Like it's like data becomes like absolutely like incredibly important here because it's pretty much garbage in, garbage out. Otherwise, right?